welcome you all to the course in application of nanotechnology in agriculture. So, we have introduced the basics of agriculture, the use of different kind of chemicals in the form of pesticide, herbicide, fertilizers in the modern day agriculture. So, this module will concern with the current state of art or state of art of nanotechnology, where we will be dealing with the classification of nanomaterials. We are dealing with the different kind of or the broad classification of synthesis techniques which are being used. The third aspect what we will be dealing out here will be the different characterization tools which have been employed in characterizing the nanomaterials, in understanding their physicochemical properties and their surface properties. So, this whole fragment or this whole module is a kind of a walkthrough with different technologies of nanoscience. So, if we see nanotechnology, so it goes back to one of the famous quotes from Richard Feynman, which says there is a lot of room at the bottom. What that essentially means is that as you really go down in terms of size, if you recollect in the very first module where I give you an explanation of how the nanostructure really looks like, if you have a bulk structure and you break it down to smaller and smaller and smaller pieces, your exposed surface areas to volume ratio is really going to go up, and that's exactly where lies the catch, that you have lot more surface for reactivity. So, in other words, in the nano domain, the reactivity of the material is exceptionally high. So, in that context, Feynman quoted that there is plenty of room at the bottom, and with the onset of modern day nanomaterial synthesis, we realize there are two broad approaches what can be dealt. So, one of the approach is top down approach, the other one is the bottom up approach, and most of the synthesis techniques are classified under these two heads, which is top down or bottom up. So, when we talk about top down approach, we are essentially talking about taking a bulk material. Say for example, all of you must have seen where wheat is being grounded to make the flour. So, what is wheat is? Wheat is a bulk material. So, what you are doing, you are putting in a mill, it could be a ball mill or it could be any other kind of mill, or it could be a grinder like this. So, you are bringing down the size of the constituent by grinding it. In other words, you are putting mechanical pressure. You are putting gigantic amount of pressure to make it powdery, or depending on what level of grain size you want, you can make it coarse, you can make it fine, you can make it very fine. Okay. Now, this could also be achieved with other material by putting thermal energy, by putting other form of energies. So, that is basically you are breaking a big stuff, a bulk material into smaller sizes, which is top down approach. Whereas bottom up approach is where you are taking small atoms, it's tough to say small atoms, rather I should say some kind of a salt, and you are self assembling them in a reaction vessel to form smaller particles by the simple process of self assembly or directed assembly or template driven assembly, all sorts of myriad of techniques which leads to assembling or clustering or coalescing of handful of atoms in a certain geometry, or maybe in a dynamic geometry. We will talk about these, what we meant by in a certain geometry or in a dynamic geometry. In a dynamic geometry, they are changing their shape, conformation, or the arrangement of the particle depending on their state of existence. Okay. So, these are the broad ways how we can look as a layman, how we can make nanostructures. So, to formally start off with, so this module will be dealing with nanotechnology, and within nanotechnology we'll be dealing with classification of nanomaterial, classification of nanomaterial, then synthesis of nanomaterial, and the third section will be dealing with characterization of nanomaterials. Now, in terms of classification of nanomaterial, these could be classified in two groups based on their shape or geometry, and secondly based on their chemical nature. Okay. If we classify them based on their shape and geometry, they could be classified under, so I am moving on to this part, they could be either called as nano cages. Okay. So, these nano cages was first reported in 2002. This kind of nanomaterial is hollow interior and porous wall containing metallic nanoparticle inside. Their size ranges from 10 to 150 nanometer. It is something like, think of a cube, so and inside it you are having the nanoparticle sitting. Something like this. Okay. So, in other words, what you have done is essentially something like this. You have entrapped the molecules inside it, and mostly it has a, as I mentioned, this class of nanomaterial is hollow interior. It is hollow, and it is porous walls, pretty porous walls, and containing mostly metallic nanoparticles are present in them, and their size range varies from 100 to 150 nanometers. Okay. So, then comes the next one, which is nanocrystals. These are of different shapes of crystals. It could be, the easiest to draw will be a cubic crystal. So, something like this, cubic shape. This basically a crystalline structure, and they are approximately 100 nanometer. Okay. Then comes nanobelt. These are ribbon like structures. Something like this. Nanobelt is thin and flat sheet of ribbon like structures that are typically 30 to 300 nanometer, depending on at what size you wanted to pitch your nanomaterial for your specific purpose. And nanobelts with rectangular cross section and well defined crystalline facets enable it to attain unique optical confinement. It has very interesting optical confinements, and it has microcavities, and it could be used for catalysis, and it has lot of piezoelectric properties. Think of it, because you can compress them. Okay, so that gives it a tremendous scope of piezoelectric features. It could be used pretty extensively for catalysis, and it has lot of these microcavities. Next is the nanofiber. Fourth one is nanofiber. So, nanofiber is a nanofibrous mesh or a network like this, something like this, and it's a 2D, mostly it's a 2D mesh, and having a diameter less than around 100 nanometers. Okay. So, each one of these having a pretty small diameter, and these could be used for different kind of biomedical application, as well as for fertilizer release, as well as several other release of active compounds. Okay. So, essentially what you are doing, you are wrapping the particles like this in this nanofiber mesh. Okay. Next is we have nanoparticles. The name itself says these are simple particles of different shape. They could have geometry like this, they could have a flowery geometry like this, all sorts of geometries you will observe in them. So, these are the nanoparticles, and there is where you can really go down with the size. You can really go down to 1 nanometer easily in these kind of particles, because you are not restricted by any kind of spreading out in these stuff. So, then you have nanotubes. So, nanotubes, as the name itself indicates, so nanoparticles are the one which typically can be reduced to 1 nanometer or maybe even less than that. That is where you have a lot of room to reduce the size. Next is the nanotube, as the tube says. So, these are something like a cylindrical structure like this. It is a microscopic tube with a diameter which is measured in nanometer less than 100 nanometer, and nanotubes are mostly hollow. So, this whole part is empty. So, you really can fill stuff into it. On the contrary, nanorod, if we talk about, it is a solid structure. So, you could have tubes in two ways, like either like this, which is solid nanorod, whereas when you talk about the tube, it is the hollow cavity moving through. Okay. Then we talk about nanowires, which is similar to ribbons though, but there are different nomenclature introduced by different people in the pretty early phases of nanotechnology. So, nanowire is a smart one-dimensional nanostructural material with a dimension of 10 to the power minus 9 meters. Okay. Then comes quantum dots. So, quantum dot is, which is sometimes represented QD, quantum dots. So, quantum dot is a nanocrystal of semiconducting material, small enough to exhibit quantum mechanical properties, and their excitons are confined in all the 3 dimensions. These exhibit strong size dependent optical and electronic properties, and quantum dot can contain few as 100 to 100,000 atoms within a quantum dot volume with a diameter of 10 to 50 atoms. So, when you talk about a quantum dot, we are talking about 10 to 50 atoms, atomic resolutions, and they have very interesting semiconducting properties, electrical properties, and they have tremendous potential, but to control their size is a real challenge. Okay. So, it is not really easy to handle anything between 10 to 50 atoms and uniformly obtaining 10 to 50 atoms over a period of time. So, quantum dot on one hand is a very promising stuff, but getting quantum dot is not something so very trivia. It needs lot of I would say practical iterations to reach to the point of obtaining uniform quantum dots. Okay. From here we move on to nanocomposites. So, nanocomposites are multiphase material where at least one of the constituent phase has one dimension less than 100 nanometers. So, for example, if you have a composite of A and B, then one of them, either the A or B, suppose I say A, so it should have that nano dimension with it less than 100 nanometer. The promise of nanocomposite lies in their multifunctionality. So, you could have the functionality of this and you could have the functionality of B. So, both could exhibit different kind of functions, and the possibility of realizing unique combination of properties unachievable with traditional pristine materials. So, essentially what you are doing, say for example, you have a composite of say B, A, C, D, and if you could really manage to get the phase conditions right, then what you are catering is a very exotic material with properties of this, 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 as well as their interactive properties which emerging out because of their interaction. So, these are some of the material which have profound application, if I had to say, in agriculture. This is what we are looking forward to in terms of having a compact fertilizer capsule, like you have say for example nitrogen, phosphorus, potash, and say boron, silicon, likewise. So, nanocomposite, the whole area of nanocomposite and confining nanocomposites into some form of say nano cages for say slow release of active ingredient, or confining them in some form of nano belt, say for example decorating a nano belt with different kind of material as we are mentioning, say A, B, C, D, E, and with the amount of surface area what is available for it to react, the rectangular cross section as I have mentioned, these could have profound impact in terms of using them as material for futuristic agriculture, both from insecticidal, pesticidal, and all other wide array of applications. Okay. So, this is basically what we talked about is the structural way of classifying nanomaterial based on their shape and based on their geometries. And there are many more small nano diamonds and all these kind of things. Then you have beads and all, but those are nomenclature. But at the end of the day, what you have to realize that different kind of nanoparticles or nanomaterials, depending on the chemical moiety which is present there, they self assemble in a unique way, and we are just in the process of understanding some of these. So, today what I have been covering out here in terms of the different shapes, maybe 10 years down the line or even 5 years down the line, there will be many more such shapes coming through, and maybe a different kind of classification which will emerge through. Okay.